Okay, so today so I'm going to talk about recent result with Theo Drivas and Inji Jiang. So you can find it on the archive. And so did anybody solve the homework problem, by the way? Solve the homework problem? What's the answer? What's that? What do you mean?
Like if you have epsilon t, then you go up, like every time you oscillate instead of going y.
That's right. Right. Okay. So I have one correct answer. So that's great. So if you take so if you're on the torus and you take velocity field sine of y comma 0, it has these two streamlines, right? So this has two streamlines, one that's pushing to the right and one that's pushing to the left. And now if you consider the perturbation, just like that, so that every particle moves. So these are actually moving a little bit up, and these are moving a little bit down. You actually get that the solution is isochronal. So phi, let's see here. So phi 1 dot is sine of phi 2. Phi 2 dot is epsilon. Okay? So you solve it, you get phi 2 is x2 plus epsilon t. Phi 1 dot is sine of x2 plus epsilon t. So phi 1 is x1 minus cosine x2 plus epsilon t. Okay, 1 over epsilon is cosine of x2. Is that right? Yeah. Does that make sense for everybody? So in particular, the flow map, which is this and this, no matter how many derivatives I take in x1, x2, it's bounded. So the gradient of the flow is uniformly bounded. Okay. So this example seems to illustrate that if you make, notice that it still gets very large. So as you make an epsilon per, then by some stability thing, you can say that you control the solution to time 1 over epsilon. But so it looks like the original solution on time scale. So for time like 1 over epsilon, so like a little constant times 1 over epsilon, phi epsilon looks similar to phi, right? You can make this statement. You know, after that time, okay, it may look very, very different. Okay. But this perturbation is not really so good of a perturbation, because, what's that? Yeah, so if it doesn't do what you want, you just say it's bad, right? Actually, there's a reason, right? So this is not actually Hamiltonian, right? So this perturbation, so if you try to write u epsilon is grad perp of psi, you're not going to find a psi that's periodic, right? Because this is supposed to be mean zero on every line. So the key point is that if you have a Hamiltonian velocity, so if I had told you the velocity needs to be Hamiltonian, you'd have to ensure that the integral of u2, so the second component, is 0 for every y when you integrate in x. Which means on each of these lines you have an equal amount of points going up and an equal amount going down. And it has to be 2 pi periodic, of course. Now what's the answer? Okay, maybe it's clear still, but the answer is that it has to grow. So let me state the theorem now. Okay, so I'll state like just keeping with what we've been doing, I'll state kind of the simplest theorem. So if u star is sine of y comma 0, so you don't need to assume this, okay? It's fine. So if u star is sine of y comma 0, and if u minus u star in x and epsilon, so I'll tell you what x is. And u is any time-dependent velocity field, just satisfying this. Then the gradient of the flow associated to u grows like a constant times t. Okay? And in fact, if you, let me explain it. So assuming u is grad perp psi. Okay? Okay, so now let me try to explain the proof. So let's just come back to the channel case. So I'm not going to come back to this really. So let's just say you have a u star. It's not the same as that u star. So say that you have a u star which has a trajectory. So u star is autonomous. So it has a trajectory on which the particles move at speed 1. Okay? So in a neighborhood, all of the particles essentially move at speed 1. And if it's periodic, then when a particle comes this way, it comes back over here. Right? So let's try to lift this picture. So let's forget that it's periodic. Well, we don't forget it's periodic, but we just lift it to the channel. So you have a periodic velocity, and you see how it moves particles starting in minus pi to pi box on R. Okay, so you look at the dynamics phi on R. So the channel is, so originally the spatial domain is a circle cross 0, 1, but you look at the flow map on this domain. Does that make sense? So how the particles move on R cross 0, 1. That's kind of natural, actually, because whenever we solve for the flow map, like this formula is not really a statement on the torus. So if I start with x2 equals 0, I get a very large number here. I get like 10 after some time, right? Which we would have to say, okay, I take it mod 2 pi. But if you don't say mod 2 pi, you have a nice formula that doesn't, wrap around. That's all I'm saying. So you just lift it to R cross 0, 1. Does that make sense for everybody? This is what we do anyway. Whenever we solve on a periodic domain, usually this is what we do anyway. Okay, then for U star, if I look at the motion of these particles, if they're moving approximately at speed 1, then the location, then these particles should be approximately t after time t. Is that okay for everybody? If they're moving at speed 1 and you wait for time t, then they'll have moved time by t, right? Similarly, if you look at these guys and they're moving at speed minus 1, then phi 1 of xt will be like minus t after time t. Okay, so you see that the fact that you have two streamlines like this, if you look at the motion of all of the particles in this box, if you look at phi t of m, the diameter of this thing becomes like a constant times t as t goes to infinity. Okay? That makes sense? So the statement that you have trajectories going in different directions, a velocity going at different speed or in different directions, is just a statement that if you lift the picture, the diameter of the lifted thing is growing linearly. Okay? Is that fine? Does it make sense, or it's okay? And we're going to prove stability of this sort of thing. Okay, so a problem that you see with this example, so a problem you encounter with this example is that a particle that starts out here, now if I look at U, there are no, if U is now time dependent, there are not necessarily any invariant curves, right? It can have any time dependence, right? So a particle in theory can go spend some time up here, spend some time down here, comes back, spends some time up here, spends some time down here. You can't make any statement like this. Not this one. You can't make any statement like this. If you start looking at particles that start in the strip, they could all leave and migrate down here, in theory. Okay? Does that make sense? Okay, so then we want to, so let's define the following quantities. So we look at integrals of this type. So you look at the integral of phi 1 f of phi 2. So you look at x's inside this entire domain, and you ask, now f here Okay, so f1 is, okay, so let's say that these values are like y1 1. Okay, let me I'll try to make it easy for you guys to understand, and we forget that there's two strips, so just look at one. Okay, so we'll only look at one quantity, and you'll see how to do it. Okay, so this is y1, y2. Okay, so f we take to be some cutoff to y1, y2. Okay, so it's not a, maybe that's bad notation. This is just a smooth cutoff. Okay, so it's like, it's just a function of one variable, like that. It's a positive function. Maybe its integral is 1. And it's supported between y1 and y2. Okay? So this quantity, say it in words, it's the average x location, x1 location of particles currently between y1 and y2. And that started in M. Does everybody understand what this integral means? So you fix a time t, and I want to know what is the x location. So I want to know for the points that are currently in this strip. So at time t, this picture, okay, maybe I'm not explaining it so well. So I take a look at this entire strip between y1 and y2. So this entire strip. And I look at the evolution of the particles that were between minus pi and pi at time t. And I ask, on average, where are they located in this strip? Does that make sense for everybody? Is it clear? That's what this integral is. What's that? Oh, there are two boards. Sorry. Yeah. Okay. Okay, now the main lemma is that lambda prime of t. So, okay, let me not state the lemma actually. Let's just try to compute it and try to see it directly. So the point is we want to compute this lambda, and if we prove that, you know, this lambda is, okay, so for u star, right? So for u star, so if you say lambda star, so if u star is autonomous, and u1 is shear flow, autonomous shear flow, means you don't have any motion in u2. Then, and u1 is approximately 1 between y1 and y2. Then lambda star of t is like 1 times t times chi of phi 2, which is just t. Does that make sense? Okay. This makes sense for everybody? Yes? It'll come. It's basically L1. Yeah, it's actually L1. But we're going to see it from the proof. Yeah. Okay. So if you consider this for the steady, for a shear flow, all of the particles are moving linearly to the right. So phi 1 is just like t. So the lambda is just like t. It's like the average location in t of the particles in that strip, right? Okay, so now let's try to compute it in the general case. So the point is to be able to write it as something that doesn't really depend on the flow, but only depends on the velocity, and then we'll be able to estimate it. Okay, so let's compute. So it's d dt okay. Okay, so the time derivative can fall here or it can fall here. So you get that it's the integral of u1 composed with phi times f of phi 2 plus the integral of phi 1 f prime of phi 2 times u2 composed with phi. Okay? Does that make sense for everybody? Okay, maybe let me, before we jump into, I should ask, like, so this sort of integral may look funny to people. Because you may think, oh, phi is preserving, and m is invariant under phi, so this is just this, right? Because, you know, you can change variables. That's not really true because we've lifted m, we've lifted phi. So this thing now is some crazy rectangle, and this thing is not a periodic function. Does that make sense for everybody? So when you compute this type of integral, be very careful not to just do the usual thing. So we'll see that here now. Okay, with this piece, actually we can do that. U1 is periodic. F is periodic in x1, right? So this is just the integral on m of u1 of x, yt, okay, x1, x2t, times f of x2. So if you know that u is close to u star, then you know what this is. Does that make sense? So this piece you can determine by knowing what u is, right? Doesn't depend on phi, in a sense. Doesn't depend on where the particles are. It's just statement about u. Well, they call it a kinematic condition or whatever. This one we can't do the same thing. So this is the main one we have to compute. Okay, so change variables. Okay, as long as I don't say this is the same as m, I'm fine, right? There's nothing wrong with this statement. When you lift the flow to R, it's still measure preserving. It just doesn't keep the original set of particles invariant. Okay. All right. Now, when you look at this, if I just brute force estimate it, so if I just estimate this term, then this is x1. x1 may be very large, right? So things are being stretched out. So this could be, in theory, of order t. Right? It will be order t times epsilon. Right? If we're making a perturbation of u star, so if we're making a perturbation of that type of u star, so not, we just think of like a shear flow or something. So if you just make a perturbation of u star, u2 is going to be small, so this will be order epsilon t, just like we saw in the counterexample. Okay, does that make sense? Okay, so. Okay, you can put it. Okay, so yes, let me. Yeah, so I should explain this point. So you can put it. But why can I remove it? Because just imagine that you have, okay, just. Right, so it becomes very long. So it can be like really wiggly, okay, okay, let's not draw that. It's actually kind of difficult to draw how it can look. But then you're integrating a periodic function. So it doesn't matter where this is. You can just pull it back to the original m. You see what I'm saying? So even if this is, minus 2 pi plus 10,000, minus pi plus 10,000 to pi plus 10,000, you can still pull it back to the original one because you're integrating periodic function. Does that make sense? So you can rearrange it so that it's back to m. Is it clear? Okay. Okay. Now this term, we can't do that because this is not periodic. So we have to be more careful. So obviously we're not going to estimate in brute force. So we're going to use the fact that it's actually Hamiltonian. So we're going to use the fact that this is d1 of some psi. Okay? Makes sense? So you don't want to, if you don't use that, you can't do anything, actually, just like the example gives. Oops. Okay, so now you do something a little bit crazy. There's going to be a lot of kind of nasty pictures. So let's just say that it's, can be like that. Okay, it's actually very difficult to draw the image of a periodic thing on the whole thing, right? If you want it to have a lot of ups and downs, it's actually quite difficult to draw it so that it doesn't intersect any image of itself, right? But let's say it kind of looked like that. Okay, so let's take each y value and integrate separately. Okay, so for each y value, so for each x2, so generically it will be that if you look at this level, there will be a finite number of intervals that are inside of the domain, are inside phi t inverse of m. Okay, so you're integrating on this thing, and you want to integrate by parts. Right? So you want to do the only thing you can do is this, which is integrate by parts in x1. But to do that, you need to know how it looks in x1. Right? So you cut it. You take each slice in x2, and you see that, okay, each slice is going to be some intervals. So, so for each x2, phi t minus 1 of m. Okay, so for each c in 0, 1, phi t minus 1 of m intersected with x2 equals c. So that's this slice. It's just a union of intervals. Okay. The left, the right. Okay? Just a union of intervals, okay, crossed with C. Is that okay for everybody? It's a little bit delicate, so you have to kind of pay attention. And the key point that you can see from this picture is that you can, so we can assume always that n is odd. Okay? Okay. So let's say you have a periodic function on minus pi to pi. Okay? So okay, I explain this point. So this curve is connecting, so these curves are connecting the bottom to the top, right? So if you're coming up, you can, okay, so maybe it's a bad, so you have one curve, so these are sides of the domain, which are 2 pi translations of each other, right? So remember what we did. We're looking at the image of this domain, minus pi to pi, under a 2 pi periodic velocity, okay? So these sides, these sides always remain 2 pi translations of each other for all time. for all time. So this one will evolve as some curve, and this will just be its translate by 2 pi. Does that make sense? Okay. So now you're connecting this point, connecting the bottom boundary to the top boundary. So you're going up like that. Say you do like that, then the other one is this. Then there's one interval. Okay? Say that you need to connect the bottom to the top, but you're going to go, right? So you go up, you come down, but then you have to go up again. And then this has to be a 2 pi translation of it. So it can go like that. Right? So then you see you have, so the point is that you have to go out, right? You can't go up and then down. You have to go up, down, and then up always, right? So then you have 3 intervals. And this is the case no matter how many times you wiggle up and down. Does that kind of make sense? So you can always assume n is odd. Okay? It's just a continuity property. That's the first thing. The second thing is that if I look at these boundary points, and I'm going to integrate, so when I integrate by part here, the point is that I get boundary terms, right? So if I look at integral from 0 to 1, integral on these sets, okay, which maybe we can call gamma c. Gamma x2, sorry. Of x1 f prime of x2, d1 psi of x, dx1 dx2. Okay, so now you integrate by parts. So now you integrate by parts. You get the bulk term. Okay. Does that make sense? You get the bulk term. Bulk term, you can, this whole thing is the integral on phi t of m, right? I actually made a mistake. There's no inverse on this. Sorry. I've been errantly writing this everywhere. It's wrong. So this bulk term is a periodic function. That's by assumption. F prime is also periodic in x1. So this is the bulk term. The bulk term is fine, actually. Right? So this term is not bounded by epsilon t, it's bounded by epsilon, so long as psi is in L1. So this is psi of the perturbation in L1 is less than epsilon. Okay, but then you also have this boundary term. So you get the integral from 0 to 1 of some boundary terms. So you get x1 f prime of x2 psi, okay, and then you get the boundary terms. And this one is dangerous because it has x1. Okay? Is what I'm saying making sense? Or maybe it doesn't make much sense. Let me start from the beginning, just to explain what we're doing. So we're trying to compute this type of integral, which tells you the average horizontal location of particles that are at time t in a strip where you know what the horizontal velocity is. Then, okay, so you differentiate it. Then you get a term where the derivative hits the phi 1, so that's to do with u1, and a term hits phi 2, and that's to do with u2. Okay? And we're trying to estimate now this one. To estimate this one, we change variables and try to integrate by parts using that u2 as a derivative in x1. Okay? Does that make sense? Okay, to do that, you need to look at each slice. You're integrating by parts in x1, so you need to look at each x2 slice and integrate by parts on that. So you need to compute this. In the bulk term, when the derivative falls on the x1, right, so the whole integral, you get this term. And that's integral you can compute without knowing what phi is. Right? You can just compute it from the stream function. And it's the perturbation of the stream function, because if we look at d1 of psi, you see if we consider this u star we're talking about, which is a shear flow, d1 of psi star is 0. So it's really only the perturbation of psi. So that's for the bulk term. Of course, you get a boundary term, which we're about to explain how you estimate that. Is there any question about what we're doing? Yes.
Question about the general philosophy. So at the first lecture, you showed that this kind of behavior with the gradient of the flow map that grows linearly is somehow generic, right?
For autonomous flows.
For autonomous flows.
Yes.
And then, okay, then you are having to show some rigorous results for flows near.
Yes, you want to say that for flows near a autonomous flow that you don't know anything about them in time, they still exhibit the shearing and all that stuff.
So these kind of theorems are conditional theorems where you say somehow, okay, if the flow is close in weak topology to my well-known flow, then we will have this phenomenon, right?
You mean if the velocity, so flow, you mean the velocity or the flow map?
So for instance, the condition u minus u star in L1 less than epsilon. So
Yes.
it's a kind of if theorem.
Yeah, which would be implied by Arnold stability, for example.
So the stability in weak norm will imply that's the general theory.
Yeah.
Weak norm will imply.
Yeah. So, right. So you want a theorem that says that the stability you get from the Arnold theory, which we discussed yesterday, so it'd be like L2 stability in vorticity or something like that, would imply that the flow map, so the motion of the particles close to the background, is very similar. Right? Yeah, that's the general philosophy. So, sorry, I didn't make it very clear. Yes?
Question, like making a perturbation which is Hamiltonian, so like basically you're perturbing the stream function, does it say that you are, say, doing a volume, like a diffeomorphism of your initial condition, like as Arnold stability is implied by diffeomorphism of the initial data, here perturbing the stream is related to perturbing the stream lines of the flow, and then
I think maybe make Hamiltonian perturbations just saying that you're not yeah, I don't know how to say it in a general sense, actually. I'm not sure actually what you're saying, so we can talk about it after. Yes.
Could we do about periodicity assumption and how we make the phi disappear? Because if we look at the sketch on the right,
This one. Yes.
interval, so I don't know how periodicity makes you go into one interval, which is m. Like this is phi of m.
So all of these correspond to intervals, unique intervals in the original circle. No, because it's a flow on the circle, right? So it's at the end of the day, it's a flow on the circle, right? So you have view this t cross 0, 1, right? View this t cross 0, 1 is annulus. Okay? So now what we're saying is that you fix a circle, fix this thing, and we're looking at the particles that are currently on the circle, where they came from. Okay? And this x1 is like a theta direction. It's kind of hard to think about it. But you cannot have these. So these three have to union exactly to this circle, right? Because the flow is a diffeomorphism. You see what I'm saying? Say that again?
Yes, maybe.
Okay, suppose that these three union to like 0 to pi. Okay, when you rewind them, when you pull them back, they union to 0. Okay, that means they union to this half of the circle. Means nothing got mapped here, right? Means this is empty, no particles here.
Particle cannot leave the circle when they are.
No, it doesn't. No. We're looking at the image of all particles in the whole domain. We're looking at image of all of these particles. Does that make sense? So you look at the image of all of the particles. So there's always particles on this curve. There's always a full set on this circle. Does that make sense? So if in this picture you say these three don't union to all of 0 to 2 pi, it means something is missing. It means there's a piece there where there are nothing. Does it make sense? And you also, by the same token, cannot have them overlap. Like you can't have this one when you take it mod 2 pi, it goes to the same place that this one went. Because that would mean that the particles crash. Does that make sense? Yeah. It's actually a very dangerous thing to do these computations, because you can really make mistakes. So it took a long time for us to convince ourselves that everything is correct. And I think it will take even longer to convince other people that it's correct. Okay. All right. So can we compute this? Okay. Okay. So this one means that you're evaluating, so this is equal, if I use this notation, it's equal to the sum from I equal 1 to n of, so x2 is not part of the integral, right? So it's just an x1 integral. So this f prime of x2 comes outside. So it's just x1 psi of x1, x2. x2 again is frozen, right? So this is the same for all of the values we're looking at. From pi I L to pi I R. Okay? Does that make sense? Now, let's come back to the picture. Okay. Say that this is P1L. This is P1R. So I'm just going to do the case of 3, and then you'll kind of see how it goes. This one is P2L. This is P2R. So you're looking at the interior pieces. This is P3L, P3R. Okay? Now, what is P2R in terms of P1L? What is this point and this point? So I told you the two curves are 2 pi translations of each other. They have to be, right? They have to be 2 pi translations of each other. So P2R is exactly 2 pi plus P1L. So this one is a 2 pi translate of this one. This one is a 2 pi translate of that one. This one is a 2 pi translate of that one. Does that make sense? It's clear? And if that's the case, you see, this one comes with a minus in the integral, right? So this is a left one. So it comes with a minus, plus, minus, plus. This one, by the way, this odd thing that I said is important. Right? So if you could have more intervals, and all of what we're saying is going to be wrong, which is also scary. Minus, plus. Okay, so if you just combine, so now if I just combine, so I'm going to get out of this, so I'm not going to write the whole sum. So I get, for example, P, so I just take these two pieces, P2R, psi of P2R, comma x2, minus P1L, psi of P1L, comma x2. Okay, and other stuff, okay, and similar stuff. So I'm going to pair this point with its opposite, which is that point. Okay? So P1L it's just a multiplication here. Okay? Does that make sense? Everybody see what I'm about to do? So P2R is 2 pi translate of P1L. So psi is periodic, 2 pi periodic. So this is P1L. Okay, maybe I'll start using the other board now. Don't. I get that, so that term I wrote down. What is it? P2R, psi of P2R, x2 minus P1L. And I know that P2R is just 2 pi plus P1L. Okay? Okay, so I just compute this. It's 2 pi plus P1L psi of 2 pi plus P1L x2 minus P1L x2. Okay? Does that make sense? Okay, psi is 2 pi periodic. So I can take this as common, and I see that one that you're concerned about is gone. Okay, so this is 2 pi psi of P1 x2. Does that make sense? So the x1 is gone because of this plus minus business. And there's another minus business because you see all of the others are also opposite, right? So the P1L comes with P1R in the opposite sign. So in the end, maybe I just now make it exercise. That the boundary term I said, so boundary term is boundary psi of x2 bv in x1 times 2 pi. Okay? And you also have f prime, so f prime infinity. Okay, again, just take the f prime out. So just the x1 part is controlled like that. Does that make sense for everybody? So it's just like you can get rid of this x in the front because by pairing them this way, and then you can now pair the ones on the same curve. So this is the first pairing we're talking about is pairing points that are on the two curves. So you pair each point on the left curve with a point on the right curve. Okay? And that gives you, instead of the x, instead of that x1, you get a 2 pi. And then you pair the points consecutively on the same curve. And that gives you like the BV thing. Okay? Does that make sense? Okay. So this is really L1. So let me actually write it. So it's maybe I just say that the average location of a point at, so in this example, okay, the average x location of a point at y equal to pi over 2. So at a point at means I take a small neighborhood of y equal pi over 2 is t plus order of epsilon t, where this epsilon is just the L1 norm of psi plus d1 of psi. So of the perturbation localized to that strip. So localized. Okay, so you only really need to know what the velocity is around those strips. It doesn't matter actually what the velocity is outside of this little region you're concerned about. Say that again?
The size of f prime when you localize.
I mean, you localize and then you take epsilon. It's yeah. But okay, if you assume higher regularity on U, which is still from the Arnold theory, you can actually prove it on the curve. So you can take F to be a delta. But then you need to take U like close in C1 alpha, in C alpha. Okay, let me mention a few consequences of this computation. And I won't go for too long. Maybe I take 20 more. Okay, so this is a, so you would say that you can take it local. Okay, so there's a local version where you just fix two regions you want to study where the particles go. And now I'll tell you this global version. So corollary. So consider, for example, the Couette flow on T cross 0, 1. So consider the Couette flow on T cross 0, 1. And assume U is Hamiltonian and U minus Y0 in L2 is less than epsilon. Then you get the following global control on the flow. So you get that phi 1 minus phi 2. So the flow of the Couette flow is x plus ty, right? So when you take the Couette velocity field, you get phi 1 is x plus ty, phi 2 is x, right? Right. So if you take this one, you get that. Now I say if you perturb it, then this quantity satisfies some inequality. So x1, L2 of m. Okay, so this doesn't say that. So this is okay. It's not just for the Couette flow. But I just want to state it simply. This says that image, even though you don't actually know where the particles are, but in a sense, the image of this domain is the image of this domain is essentially the same as the Couette. So if you unwind the actual image, right? So this is phi t of m. So if you unwind the actual image by the Couette flow, you get something very close to the box. Does that make sense? But it doesn't matter. We're not saying that each particle stays on its streamline or anything like that. You're just saying that the image of this looks essentially like the image of the Couette flow, but particles can be moving along the rectangle. Is that clear for everybody? And you can prove that Okay, so the vertical motion in the average, so certainly with an epsilon perturbation, if it's not autonomous, you can take a particle. So in the Couette flow or in a shear flow, will stay on their same level, right? So the particle just moves horizontally, right? Doesn't move vertically. And you could, if you look at a single particle, make a perturbation so that it kind of goes, it's like it schemes against the flow, so that it moves in time 1 over epsilon, order 1 away, no, in the vertical direction, right? You can, it's easy to do. But on average, it takes much longer than that, so it takes exponential long time. Okay, so let's do t. And this is for t large. Okay, so the time it takes to diffuse on average is like exponential of 1 over square root of epsilon. Okay, even the point is that this is true for even non-autonomous U.
Sorry?
Yes.
You sometimes use x1, x2, and sometimes x and y.
Yeah, sorry, yeah. Sorry. Apologies. Yeah, with the flow map, I don't like writing phi x and phi y. It looks like a derivative. Is there any question about this statement, or it's clear for everybody? The proof of this is much more direct. It's really energy. So this you feel much more comfortable with. There's no like counting number of points or anything like that. It's just direct estimates based on the calculation we did. Okay. Let me give some examples now, some corollaries. So as I mentioned yesterday, one of the small drawbacks of the Nadirashvili point of view is that you really have to use the boundary, and there's sort of no way out of that. So in here you don't care. I mean, in the computation I showed you, you kind of care that there's a boundary, but you could also have done it on the torus. You have to modify a little bit the argument, but it's essentially the same. You have to take the initial set of particles to be infinite in the x2 direction. But so now we recall that the so omega is sine of y. As we said, is a steady solution of Euler of 2D Euler on T2. That's not the application. just a fact. So this is a steady solution of 2D Euler. We restrict to solutions, and we mentioned yesterday we don't know if it's actually Lyapunov stable. We restrict to solutions that are odd in Y. Then you annihilate the potential instability. So you annihilate cosine of Y, cosine X, sine X. Then it's Lyapunov stable in the sense that if omega 0 minus sine Y is less than epsilon, then omega of t minus sine Y is less than 10 epsilon for all time in L2. And you can do this in any LP, but L2 is good. And that implies that omega of t, the flow map, the velocity field vorticity sine y is coming from velocity cosine y comma 0. So u of t minus cosine y 0 in W12, so in H1, is bounded by 10 epsilon for all time. Okay, so this is a consequence of the Arnold theory. Okay, then we know that theorem. So consequently, look at the flow map for any function, any initial vorticity close to sine of y. The flow map must satisfy a similar estimate to what we wrote there. So phi 1 minus t cosine of phi 2. So this is the shear, minus x1 in L2 is less than epsilon, square root of epsilon t for all t. Okay? Now, so that's a statement about the flow map. We want to make now statements about the solutions. Okay? So now suppose, so I'm looking at solutions that are odd. So this is y equals 0. This is y equal pi. So it's odd about 0 and consequently odd around pi. And the vorticity has to vanish on these two things. So, okay, it would be nice if we could just connect these two with level sets that are different and then show that they separate like that. You can't do that because the vorticity is 0 here and it's 0 here. Okay? Does that make sense? So all you do, because now you have a bit more power. So the cosine of y, by the way, it goes like -1 here, and it goes like plus 1 here. And in the middle, it goes from 1 to minus 1. Okay? So for any velocity field, it'll just be a perturbation of that. Okay? So now I take level sets. This is minus pi to pi. So this is in the original coordinates. It's just the torus, but I restricted because I have a symmetry in y. This is now, these are now fixed curves. I can't really do anything with them themselves because vorticity has to vanish there. But what I can do is take two level sets like that. So I make a perturbation of the vorticity so that it's 1 here, 2 here, and so that in L2 it's very close to sine of y. Okay? Does that make sense? So it's in L2 it's very close to sine of y. So like I said before, you just like two very sharp mountains and you put it on top of sine of y. Does that make sense? And now you have this. So this tells you, so this implies that there exists a fixed, say, order 1 measure set of particles that when you lift it so that phi 1 of x comma t is bigger than, say, 1 over 10 t. Right? So essentially all of the particles in this region, so remember it's 1 here minus 1 here. So all of the particles, say, in this region, on average, go to the right. Right? And similarly, there's another fixed. Okay, so the fixed means, maybe fixed means the size. It doesn't mean the particles. So there exists an order 1 measure set of particles where phi 1 of xt is less than minus 1 over 10t. And those are coming from up here. Those are here. They don't know where they're coming from, but there's some fixed set of particles, sorry, this order 1 set of particles that go in opposite directions. Does that make sense? But if I choose these level sets to be sufficiently big, depending on epsilon, this is fixed. So this is like, you can say 1 over 100. Independent of epsilon. And if you take this enough, you will know that there exists some from the inside going to the left and some from the inside going to the right. Does that make sense? Because the area of the inside is preserved and it's almost the whole area. Is that clear? And then you deduce that necessarily the solution itself has to grow. And even in L1. Does that make sense? So, okay, I already went over time, so because I was late. So I won't say like everything. I just give kind of a hopeful feeling that one hopes that you can use this sort of idea to give more information on long-time dynamics, like about mixing. So this sort of estimate gives you some feeling about, so there's actually a way you can say that if you make the right type of perturbation using this sort of, that at least it gets mixed in the sense that Michele was saying yesterday, to a very small scale, like order, say, epsilon. And then it would be nice, so the correct estimate you have here is actually the time integral of the perturbation. And when you're doing mixing, you expect that this should decay. And this fact that the flow looks like this should be also giving you some amount of mixing. And then perhaps you can use it to study problems like that. That's maybe, I won't claim more than saying perhaps. So, thank you.